Hello everyone, my name is Asad Mirza and I'm going to be presenting this ANSYS workshop for finite element analysis on behalf of Alpha AEMB Beta. And a little bit of background on me, I am a PhD candidate in the biomedical department working under Dr. Sharon Rasami, and my research primarily deals with aortic valves research, and it's mainly to do with calcifications on the aortic valve. And part of it is I do finite element analysis research as well as CFD computations on it to see if I can predict incidence of thrombosis. So generally that's just a lot of computational stuff, coding, MATLAB, ANSYS. Hence why I'm going to be doing this workshop, and hopefully you'll learn a little bit about it. So without further ado, let's begin. First thing, how do you actually get ANSYS? So there are two ways. First is you can get access to the ANSYS student version. This is a free software suite that ANSYS provides to students, and you can use it for homework, capstone projects, student competitions, anything academic or educational related. It only supports Microsoft Windows 64-bit, and the current release is ANSYS Studio 2021 R1, and if you get it, you can get ANSYS Mechanical, which is for structural analysis, ANSYS CFD, which is for fluid simulations. It also includes what's called ANSYS Autodyne for what's called explicit dynamics. So that's just a fancy way of saying things are moving really fast. So if you want to simulate like a bullet impact, a blast, a crash, car crash, stuff like that, that would be explicit dynamics. It also includes its own CAD software called ANSYS SpaceClaim, which is like SolidWorks and Fusion 360, except instead of it being parameterized, it's a bit more free flow. You'll see what I mean when I get to it. And it also includes ANSYS Design Explorer. So if you take statistics courses, it's like running a design of experiments on your models where you have parameters for like edges, shapes, inlet conditions, everything, and you just run a gigantic parameter space looking into how they're all related to each other. So where do you go to download it? You can just look up ANSYS Academic Free Student something, which is this link here. And the site looks like this. So ANSYS Free Student Software, you just click ANSYS Student, and you can download. Easy as enough. Now there are limitations on it. So you're only limited to 500,000 fluid cells or 128,000 elements for structural analysis, similarly for the explicit. But beyond that, there is no real other limit. So if you're fine with having these limits in your model, then you can go ahead and use this. Otherwise, you can go ahead and use the second thing, which is through FIU. So you can actually access ANSYS through FIU's remote computer access, which lets you essentially get access to the lab computers as if you're sitting there on campus. And to access it, you need to follow the details found here at eicfiu.edu services remote computer access. You're also going to need to have the dual factor authentication enabled on your account, and you have to know what your EIC login and password is, and you have to be using the VPN for FIU if it's outside. Now, all these details are given in this link. And if you follow this link, actually, let me quickly just make it primary. If you follow this link, you'll arrive here, and you can just follow this nice little YouTube video that explains how you can go from the beginning all the way to actually accessing the computers. And you also have to make sure you have that FIU VPN, which is right here, and then you follow this to learn how to install that. So once you do, you can get access to it. Now, before I continue, any questions?
The FIU VPN, does it have other features as well besides ANSYS you can access?
Oh, so it's literally like you're sitting at the lab computer. So if you can take a look here, you can see like SolidWorks 2020, you can see Wolfram, MATLAB. So any software that you would normally find on the lab computers when you're at EC is what you would have access to here, because you're actually accessing that one of those computers.
That's good. Thank you.
Yeah. And this is not like Citrix. It's completely different from Citrix.
That's good to hear.
Yeah. All right, moving on. What is finite element analysis? So is it a way to make pretty pictures? Is it an example of garbage in, garbage out? Is it a powerful simulation analysis tool? Is it a mathematical tool for solving boundary value problems? The answer is all of the above. And in the wise words of Boromir from Lord of the Rings, one does not simply perform finite element analysis. There is an art. So given that, let's first take a look at a big picture view first. So the idea is in finite element analysis is you have this giant complicated problem, you break it up into a bunch of small pieces, and these are called a finite number of elements. You simplify each piece in terms of the math. So you have a small little piece and you know what forces are going in, what forces are leaving it. and you know that, oh, whatever comes in, what must come out, continuity and such, you reassemble all this connectivity into a gigantic matrix, and then you solve this using basic matrix math, element inversion, things you learn in linear algebra. And this way you can solve how the displacement forces and stresses are in your model. And mathematically, what this means is that you know what the forces are on your object, so you know where the loads are, what part is being constrained, and you know what this K is. So K is your stiffness matrix, and what goes into the stiffness matrix is like material properties, so you know what parts behaving linearly, you know what parts is hyperelastic, you know material information about your model. And what you want to know is, okay, what's the relationship between the forces and the stiffness in terms of the displacements in my model? And that is what you're trying to find. And the way you do that is you can just invert this matrix and figure it out and isolate this D. And that will tell you, oh, this part of your model is going to displace by this much, the stresses are highest over here, so on and so forth. So from the user perspective, it's a bit different. The way it works is first you define your model. So what do you know about what you're trying to look into, and what do you want to know? Then you have to create your geometry. So it can be a simplified geometry you made in CAD, and then you naturally need to know what the material properties are for whatever you're looking into. Then you need to know where your loads and constraints are. So I want to place 10 pounds of force here. This part is not moving. So for example, in this image right here, you have a load being placed on this edge here. This part is not moving. And then you mesh or break up the model into these little elements. Then you pick what type of analysis you want to do. And then you submit the job to the black box of the FEA solver. And then you look at the resulting post-processing you want to do. So for example, in this case, is looking at the stresses. And you can see here on this curve bend here, you're getting a stress concentration, because if this part of the wall is not moving, this part is moving down, it's going to compress this region right here. So you should intuitively expect there would be a stress concentration here. Now, maybe this amount that you're seeing here is below your threshold, in which case that's great. Or maybe this amount is not good, so you're going to go back and adjust the geometry and see what you can fix and edit and to improve this model. And then you just rerun your simulation over and over again until you meet whatever criteria. Now, what I mentioned back here is this black box. What is this black box? So, and the equation you want to write is the force is equal to your stiffness matrix times your displacements for each of the little elements that you're trying to solve for. And you need to know the continuity. So the input of one is the output of the other. So you're going to link the loads and displacements of each element to the next. And so when one part gets stretched, the other part moves with it, and that moves the part that's connected to it, so on and so forth. Then you apply your boundary conditions. Loads on one end, this part is not moving, this part's moving rotationally, there's gravity, whatever. Then you solve your solution by inverting this matrix. So I want to figure out what the displacements are of our model. So I invert this stiffness matrix and move it over to this side. And now I can solve for displacements by just inverting the stiffness matrix and multiplying it by the forces I know. And voila, then you just post-process. So you can turn your displacements to strains. From strains, you can figure out where your stresses and such are, because now you also know the material properties. And from there, you report and improve. So basic FEA terminology first. As I was saying, this is boundary condition. Elements are these little triangle pieces here, although they don't have to be triangles. Each little node here is actually a shared element. So for example, this element, this triangle element here has this node that's in common with this element and that element. And you have forces here, which are called nodal loads, but you can have other types of loads, rotational, gravity, so on and so forth. And now it becomes a more bigger question: why simulate? So when you run into a problem that you want to find a solution for, usually the first thing that many people try to do is see if there's some analytical solution for it. No need to reinvent the wheel, really. So the downside of this is that this really only works for simple cases. So maybe you can analytically find a geometry solution that says, oh, if you have a beam that is this long and you have a load that's this much on this end, and you assume this part stays the same, you can expect it to bend this amount and the stresses to be about this much. However, that requires a lot of assumptions. It requires you to assume that's a perfectly straight cylinder or a perfectly straight rod, or if you're trying to do something like Poiseuille for CFD, then you have to assume, oh, there's no height difference or whatever, or there's no changes in geometry or anything. So this is really limited, but it's often a good place to start when you're doing your work. The next best thing you can do is experimental. So this involves actually setting up your actual design, making it and everything, putting sensors on it, transducers to measure pressure, flow, displacements, whatever. And upside this is that it's very accurate because you're actually testing your actual geometry. Downside is it's very limited in scope because you are only working on a single geometry, single values for alerting conditions, and you can only record data from wherever you have sensors. And it's also very expensive because you actually have to build it. Now, the next thing you can do is computational. And the nice thing is that this can be just as accurate as experimental, and assuming that you've given it a good amount of detail about the real model. But usually it's cheaper and provides way more information than the experimental could ever give. Because while the experimental might be able to give you information about forces on one surface or one part of the surface, the computational can give you information on what forces and stresses are all over your model, let's say. So with that, does anybody have any questions before I get into how ANSYS goes into all this? All right. Moving on. So ANSYS is an engineering simulation software designed in 1970 by Dr. John A. Swanson. Originally, it was meant for FEAs, of finite element analysis of structural problems. So you can consider FEA to be ANSYS's bread and butter. It's what they're best at. But they can also do fluids, electronics, semiconductors, embedded software, multiphysics, optimizations, biological simulations. They can do pretty much anything under the sun at this point. And here's some examples. So you have a mixing vessel of two different fluids. So you can see this little rotating shaft and everything. This is a TAVR valve, so this is a transaortic valve replacement procedure placed into a heart. And so this is a bioprosthetic valve, and you can see how it's functioning in terms of velocity and stresses on it. So this is manual replacement, and this is using a TAVR approach. And you can see the comparison between both. This is very similar to the work I'm actually doing. Next thing you have is this phone drop test. So on the left is without a phone case, and on the right is with a phone case. So you can see here the stresses are actually much larger without a case than with one. And you can also see here the accelerations that you can get are much more varied without a case than with one. So I guess this is evidence that you really should have a phone case on your phone. You can also do things, for example, truck design and deployment optimization. So if you have a car behind another car, how much spacing do you need to reduce drag effects and such? So you can easily test that in ANSYS. You can also do car crash simulations, as I mentioned earlier. And in this case, this is the shell of a car, and it's colliding with an infinitely stiff wall. You can see what stresses are and which parts of the frame are bending and breaking. And so you can design and optimize the shape to minimize or maximize the deterioration wherever you want them to. You can also do bullet simulations or crash simulations. So in this case, it's a bullet connecting with a piece of wall and then seeing if you can break through it or not. And these are all just sort of examples that I want to show you guys. So now to get into the nitty-gritty of actual ANSYS. So but before I do, any questions? All right. So when you first start up ANSYS, you'll run into what's called the Workbench. And the Workbench has a couple of components on it that you're gonna want to get yourself familiarized with. On the left, you'll have all the toolboxes, so you can see your fluid flow, harmonics, magnetics, rigid dynamics, static structural, thermals, all that's here. And in the center is your project schematic. So what you can do is you can literally just drag and drop these little components into your project window, and you can get these little boxes showing up. Now, on the right here, it'll give you information about the properties of this object. So for example, what type of analysis you're doing, how you want it to import CAD, and a bunch of other stuff. If you have any messages or warnings or errors, that will show up in the center here in messages. It'll also give you information on progress. So how's your meshing coming along, how's your solving, and all that's given in this progress window down here. Now, let me quickly show that to you. So here's the one I have prepared for this lecture. So you can see the static structural component here. You have your engineering data, which is like your material properties. Then you have your geometry, so anything you make in your CAD. And then this leads to your model, where you actually do your meshing. This leads to your setup, where you apply your boundary conditions and all your constraints on your model. Then you actually solve your model, that black box we were talking about. And then you do your post-processing. So you see stresses, strains, so on and so forth. And if you want to add a new thing, you just drag, drop. Easy as that. Now, let's go ahead and see the very first component of this, what's called static structural, which is this engineering data. So if we open this up, we'll get met with this little window. So let me go back here and explain this. So what you just saw was the engineering data manager, and this is basically how you can control all the materials that you're going to be using in your project. And ANSYS has a built-in list of materials that you can quickly access, or you can make your own custom materials using the drop-down menu on the left by literally just dragging and dropping as we did with components. By default, ANSYS sort of assumes everything's made out of steel. So the very first material you'll always see is structural steel. And if you click structural steel, you'll see like, oh, it gives the density, it'll give you the isotropic elasticity, compressive strength, tensile ultimate strength, various material parameters related to structural steel. And then you can see here on top right, you can see, oh, if I click ascend curve, then I can see the values for the cycles and alternary stress. And you can edit that if you want because it's just a table. And also on the bottom right, you can see a little chart of how this data looks like if you want to edit it from here. And what you can also do is have access to ANSYS' 700 built-in materials that cover pretty much anything you could possibly think of. So for example, if you went to, say, start simulating using something that you 3D printed, so usually if you're printing 3D printed something made out of PLA, well, that's one of the built-in materials, polylactic acid, that ANSYS has. And if you want to know more about the material itself, then you can just click this link and it'll give you a nice little overview of where they got the data for everything. Now for us, we're going to be dealing with some of these as well, but before then, I want to talk about how we can actually deal with our geometry. But before that, any questions on this engineering data stuff?
So if I understand correctly, engineering data is kind of like the task manager.
Sort of. Engineering data is literally just like a little repository that holds all the material information. So for example, let's say you had like, I don't know, iron. And ANSYS has iron built into it. So you could look it up into engineering data resources and try to find iron here. But otherwise, you can literally just say, okay, I know what the density of iron is. So I drag density onto here, and I'll just write whatever the value is. And then you can say, oh, I also know what the isotropic elasticity is. So the Young's modulus Poisson's ratio, that you can put that here. And say, oh, I also know what the bilinear isotropic hardening is for iron. And then you can put that value here and here. And then now when you run your simulations in ANSYS, you can point ANSYS to this material you just made and tell it, okay, use this material for your solving. That's pretty much it.
Gotcha. So it's kind of like a library.
Yeah, with either pre-built stuff that you can literally just drag and drop or make your own custom materials following any one of these many properties.
Sounds good. Thank you.
No problem. All right. So first things first, you're going to need to have actual geometry. So how do you go about doing the geometry? There's two ways. You can either import geometry from outside or use these two built-in CAD software, one's SpaceClaim, one's Design Modeler. And let me quickly go over what they are. So let me go here. So the first one is called Design Modeler, and it's an older version of the CAD software that ANSYS uses. It's highly similar to SolidWorks in that it's one after the other, or Fusion 360, where you do one thing, extrude part, sketch, next part, next thing, next. And it's built up in this tree format. But the cons of it is it has a sort of a clunky GUI that hasn't been updated in a while, so it's hard to learn this. So it's legacy in a way. And if you make an improper edit to one part of this tree, it can invalidate the rest of the tree, which I'm sure you guys have realized in either SolidWorks or Fusion 360. If you suddenly change the dimension of one part up in your tree too much, it destroys the rest of the tree. That can happen here. And because it's so old, the future development is at risk, and I actually think ANSYS is going to be removing this down the line. So what does ANSYS suggest you use? It suggests you use SpaceClaim. So SpaceClaim is a direct editor instead of parameterized editor, meaning there is no actual tree per se that you're editing. It's all just a single object that you're actually extruding or filleting or editing. And the nice thing about this is you're not actually going to be invalidating any sort of design tree because there is none to begin with. It has a very easy to learn GUI because 3 basic commands, which are pull, push, pull, move, and fill, actually make up 90% of everything you do with this geometry. You can also undo, cut, paste, and it's very intelligent. Downside is that it's a bit buggy in terms of connectivity with different assembly objects. It's not the best when you're working with slivers or very small little dimensional features, and it's still in development. So it does have some bugs, but it's very versatile and great to use. So what I would suggest though, I would suggest you make your CAD software in whatever software of choice you have. So for example, if you prefer using SolidWorks, make it in SolidWorks, then import it. If you prefer Autodesk Fusion 360 or something, make it in there, export as a step file, and then import to ANSYS. But if not, learning SpaceClaim is pretty interesting as well. Now, let's get to the nitty gritty about what we're going to be doing today. First off, I want to iterate to you guys, you simulate for a reason. You never simulate to get pretty pictures or just because. You always simulate to answer a question. So you simulate to answer a question that you normally can't because you'd have a resource constraint. So the material you want to test on is very limited. You're financially constricted, meaning you don't have funds from your sponsor or something. You're time constrained, so you don't want to waste weeks of time setting up everything for your model and everything to actually get your data. You just want to quickly test a bunch of different things at once. And so here's how the workflow usually goes. You have a problem, you make a geometry of your model, you simulate what your problem is trying to do, you analyze your results. Did you find a solution to your problem? If you didn't, make your adjustments either to your boundary conditions, your geometry, material properties, whatever is applicable. Then you have your new model, you simulate that again, analyze, did you find a solution? No, keep going around this loop. If you did find the answer, great, question's answered, and you probably saved a bunch of money and time. So with that being said, what we're gonna do today, we're gonna go right into a very interesting example of cold metal rolling. So the question for us is, when you cold roll a piece of metal, how much deformation can you expect in each direction? Now, if you don't know about cold rolling, the gist is that you have this piece of metal that you squeeze through these rollers, and what happens is that by being forced to go through these rollers, it compresses and stretches in two other directions it has, and this actually stiffens and hardens the object on the piece of metal you're rolling, as well as makes the object thinner, so you can work on it. And what we want to do is, okay, create a roller and a piece of metal, adjust the roller to be just at the edge of the metal, as would be done in a factory. Then we want to simulate this roller moving over the object, and we want to measure how much does the metal actually change in its dimension before and after rolling. And then we want to look at what the internal stresses are and see if there's any adverse localizations, and as well as how much deformation we're getting in each dimension, meaning how much actual workable metal we're dealing with after the fact. So any questions on this?
Yeah, so more of a technical question, but how do they make sure the metals that make the rollers do not deform while pressing on the other metal? They just choose a harder metal, right?
Yeah, so generally you want to use a metal that is orders of magnitude stiffer than the one that you're trying to roll in the first place.
Right.
Yeah, and that's pretty much it. Now, naturally, obviously, whatever metal you have is going to deform both ways, but one is going to deform more than the other. So first things first, the engineering data, so material assignment. What material are we going to use? Well, the metal we're going to be using is aluminum. And for aluminum, we're going to be going with a bilinear plastic model. And the way this works is it's going to behave elastically up to a point in your strain, and after that, it's going to behave plastically. So up to a certain point where you apply a load, it can spring back and be normal. But if you go beyond that amount, it's going to permanently deform and go into a plastic region. So that's called bilinear isotropic hardening in ANSYS. And so let's first go ahead and make that model. So double click this engineering data, and I'm going to go ahead and delete this iron thing here. And we're going to make one called aluminum. I think that's how you spell it. So let's give it a density, and let's give it a, where is it? Bilinear isotropic hardening. Okay, so we're going to need to give it what the isotropic elasticity is and the bilinear isotropic hardening. So the density I found online was 2,770 kilograms per meter cube, so 2770. And you can see now that I've entered it, it turns from yellow to white. Young's modulus is being defined as 71,000 megapascals. So I changed the units here to megapascals. Poisson's ratio is 0.33, 0.33. And bilinear isotropic hardening, I need the yield strength and the tangent modulus. So yield strength, tangent modulus. And those are also given in megapascals. So I have it set to 280, and 500. And these are in megapascals. So 280, 500, and that is it. So we've already set up our material. Now we need to set up our actual model. So here's what I suggest you do. In terms of the best results to the worst, I guess, if you can, make it directly in Design Modeler or SpaceClaim because it's ANSYS built in, so it has the most chance of working best. Second best thing, make it in SolidWorks, AutoCAD, CATIA, whatever. And then export that as a step file and then import that into ANSYS. And the worst thing that you can do is have an STL file and then give that to ANSYS because it can work with it, but you're gonna have a fun time processing this into an actual workable model. So how does our model actually look like? So it's going to be a roller with a diameter of 400 millimeters. It's going to be away from the slab material by about 30 millimeters. And this actual piece of slab metal, this aluminum, is going to be 1000 by 250 by 100 with a fillet of about 10 millimeters on one end. And the surfaces should just be barely touching, as you can see here. Now I already have it here. So, and this is what SpaceClaim looks like. So you can see here your metal, and you have your roller, and might as well, since I'm here, show you a little bit about this. So each of these objects is part of this little thing here, and it's not actually tree based, so there's no like, oh, I made a sketch and I extruded it and the history is here. It's all just inside this object. So if I wanted to, I could literally grab this face and then move it, and you can see here I have a little dimensional information of, oh, do I want to extrude it this many millimeters, this many millimeters, do I want to remove it this much, so on and so forth. So let me undo that. And you can also do things, for example, just casually add fillets to any part of your model. You can also do things, for example, let's say I want to fill this, and if I click this fill tool, it automatically gets rid of the fillet. Or let's say I want to move something. So let's say I want to move this face. It just moves it right up, right down, whatever. And yeah, it has a bunch of other tools you can use, but those are the major stuff. Just wanted to show you this while it's here. So this is what our geometry looks like. So we can go ahead and right click this, click import geometry, click browse. And for me, I know that this geometry is located, let me quickly find this, right here. So if everything went well, you can see this check mark here. So now we're gonna actually have to mesh the model. So click this model, click edit. I don't need this anymore. So now we're gonna do meshing. So what's the purpose of meshing? So you want your computations to be done on discrete little locations within your domain, as I discussed earlier. And the elements that I was talking about, those little triangles or whatever, they can actually be a number of different shapes. The most common ones are called tetrahedrons because these tetrahedrons are what's called unstructured, so they can fill in very complex type of shapes. But you also have things like hexahedrons, you have pyramids, you have prisms, many different shapes. And you have your original geometry, and you mesh it, and then you have your mesh geometry. So a question that often gets asked is, how much detail do you need to put into your meshing? And can you remove any unnecessary stuff in your model to make the mesh easier to do? And a general thing that I'll advise is that the more details you have in your model, the more problems you're going to run into. Case in point, for example, let's take a look at this little geometry piece right here. It has this curved edge here and then the sharp point right here, which is a recess. And because of this abrupt change from curvature to this straight edge, when ANSYS tries to mesh this, it wants to resolve this weird discontinuity in the geometry, so it puts a very fine mesh in this location here. Now, truthfully speaking, is this little dot of a recess really important in your model? If it isn't, then just get rid of it, and you can save on many mesh elements in the long run. Case in point, you should also refine wherever you expect to have large stress concentrations. So, for example, if you expect this bolt hole to have a lot of stresses because it's a bolt hole, it's what's keeping your structure intact, then add more of a mesh around this hole. If you have if you're doing a fluid analysis, then maybe you want to know what the interaction is of the fluid right at the wall. So you can add more layers here, which is called a boundary layer. So you can add more mesh layers right at the wall. And now it becomes a question of efficiency. So do you want to add very many more elements to your model? Because if you add more elements to your model, you're going to increase your computational resources. But if you don't have enough elements in your model, then you're not going to get that accurate of a solution. So you sort of have to balance fidelity with resources, and it's a bit of an art how you go about doing this. So if you take a look at this top geometry here, it's a very coarse geometry. You have this fluid domain in blue and this structural in gray. And if you take a look at the result of the fluid, it looks like you have this inlet coming from the bottom here and then separating to these three components here. But it looks like the flow is not in the center, it's actually sort of in this block region here, and then it deviates. But that was likely just an artifact effect because your mesh is not fine enough. So if you actually add these boundary layers I talked about in the previous slide, now when you do your simulation, you can see you get a large velocity of flow in the center, which is what you would expect. And most of it actually compounds towards the center. And as you get closer to the wall, it decreases in speed, which is what you should be expecting up here, and what your intuition should be saying to you. And as far as the side pieces go, you don't really see too much of a difference. It's mainly in the center where the major difference is here. So in this case, meshing was done to improve your model without sacrificing time or resources. Any questions before I continue? All right. So when you're meshing, here's the ANSYS window that gets opened up. And you can see here, you have a little check mark next to your geometry. You have a check mark next to your material, and there's that aluminum we just made with the bilinear isotropic hardening. And you can see here we have connections made. So what part of this geometry is connecting with this other? And it looks like ANSYS automatically figured out that I want to connect this roller to this piece right here. So it automatically made a little connection piece here. We'll get back to this very soon. The first thing we want to do now is this meshing. So by default, if we just click generate a mesh, ANSYS will try to make a mesh based on what it thinks is best. And oftentimes what ANSYS thinks is best is not really the best. So by default, it says, okay, the physics preference is mechanical in this case. And the default element size is based off whatever the smallest detail is of your model. And that's how it figures out how to apply your elements. But how do you know that this is a really good mesh or not? Well, you can go here into statistics and you can see, okay, this is 835 elements and the nodes are this many. But what you really want to look at is what's called element quality graphs. So if I click in this display style and click element quality, now I have a pseudo color representation of my model. And in general, element quality shows how skewed these elements are from a perfect shape. And what I suggest is the closer to 1, the better. So you can see here, not too good, especially on these fillets. And I would suggest you change and get a more nicer mesh. So let me quickly go here. So if you have a high geometric complexity, you're going to get a distorted mesh. So the skewness that you can measure goes from 0, which is excellent, to 1, which is unacceptable. And the orthogonal quality, which is what I just showed you, has the exact reverse. So 0 is bad and excellent is 1. And case in point, if you do an element size, so the default is about 70 millimeters in the geometry I just showed you. This is roughly what you would get. So very bad element sizing down here, better on the edges or something. But if you reduce the element size to about 10 millimeters instead, meaning the maximum element that you're allowing in your model is 10 millimeters, then suddenly you get mostly element quality of 1 with a smaller 0.85 on the limits here. So what I recommend is measure elements at a size that gives you generally high element quality in the regions you care about. In this case, we care about the entire region, so the entire region should be green bluish. So if I go ahead and do that, give it a little bit of time to mesh. And there's our mesh. Oh, one thing I want to emphasize here is we don't really care about the deformations of the actual roller itself, so we don't need to simulate the roller. So what I would say is go back up here into geometry and click on the first geometry piece. I believe that's this roller here. So if I click this and say, instead of it being a flexible object, it's going to be rigid. Yeah, there it is. And by rigid, ANSYS isn't going to actually solve for any deformations or anything on this object itself. So it's going to sort of ignore it beyond just spatial effects. And while we're here, the second component here, this aluminum, this is going to be flexible, but the material for it, let's switch over to that aluminum that we had made. And now that we're here, I might as well talk about this contact region. I quickly remesh actually. There we go. All right, so this contact region here, let me go to display. So we have this roller here, which is the contact body, and it's touching this face right here, which is the fillet of the metal, when in reality, it should be connecting and theoretically touching this face as well as this face, and this face, and potentially this face as well. So what I'm gonna do is click this face. This is fine. And the target is going to be all of these faces. So by double clicking on this surface, it automatically selected all tangent faces. And I'm going to click OK to this. And instead of it being bonded, I'm going to say this is frictionless. Now, why is it giving an error here? Let's go ahead and delete this. Create a manual contact region. Frictionless. Target. It's going to touch all those faces. And let's adjust how it's going to be touching it a little. So in normal stiffness, let's make this relatively stiff. Let's make this 10. I think an interface driven, so how should it be touching it? We're going to edit this to be just a touch. So ANSYS is going to move our model so it's just barely touching this piece when it starts the simulation. All right. Okay, with that done, how are we going to actually set up our model? So we're going to make it so that the roller is going to move 1,200 millimeters going forward like this in the X direction. The slabs, meaning the slab here, here, and this bottom face, are going to be constrained from moving parallel to them. So meaning, for example, this face right here is going to be allowed to move in the face in the direction normal to it, but not in the other two directions. So this is the B face, so it's going to not be moving in the Y, but it's allowed to move in two other directions. So by doing these constraints, you're going to allow this slab to be smushed, essentially, and then we're going to be able to see what the deformations are. So let's go ahead and apply these boundaries. Insert. Where is it? Displacement. We're going to click that face right there. And you can see here, X is facing positive in that direction. And what we're going to do is it's going to move 1,200 in that direction. And it's not going to move in the Y, and it's not going to move in the Z. And then that's all the issue. I was wondering why this wasn't checkmarked. The contact and target faces were swapped. So now it should work properly. All right. Now insert remote displacement. So this is the face that's facing in the Z. So if I click this face, I'm not going to allow it to rotate any bit, 0, 0, 0. But I am going to allow it to deform in the Z dimension. So I'm going to say it's free in the Z, not in the Y, not in the X. And likewise, if I duplicate this and I change it to this face, this is the face that's facing in the X direction. So I'm going to allow it to deform in the X, but not in the two other dimensions. So I'm going to say in the X direction, it's going to be free, not so much in the Y or Z. And then I'm going to duplicate this again. And now this top face. And what I'm going to do here is this face is normal to the Y. So I'm going to say, okay, this can move up and down. So it's going to be moving normal to the Y. So it's going to be free in the Y, but it's not going to be free in the X or in the Z. So it can just move up and down. And I think that should do it. And as far as analysis settings go, what I would suggest is you turn this large deflection on. And I also suggest you turn auto time stepping to on. And I would say start with a large amount of substeps. The minimum can be about 10, and then the maximum, just to make it a big number, like 1,000. And what I'm telling ANSYS is, when you're solving this matrix, take 100 substeps to figure out where your solution is initially. And if you must, go all the way up to 10,000 to get your final answer. And with all this ready, you can click solve and actually do your solution calculation. But that might take a little while. So instead, what you would usually see is a graph that looks like this, where you have your force convergence, your force criteria, and as your solution goes, in this case, I'm doing it for 1 second. As it goes along, it's going to slowly approach 1 second, which would be 100%. And once this is done, you'll have your solution. Now, I've already done this before, so I do have the answers or the solution already processed. So let me open that up. Let me close this. And it's right here. So let me right-click results, edit. Now here's the exact same model, but with everything solved. So you can see here we have our geometry, which is rigid. We have the same material. We have aluminum alloy, bilinear electron hardening. We have the same contact, frictionless. The factor is 10. In this case, I put a stabilization factor as well, and a pinball radius, so just a touch. Here's the mesh. It's not the best, but it will work for now. I did a remote displacement in this case, so 1,200 millimeters in the X. And then displacement was constrained in one dimension and free in the others. As expected. Oh, it looks like I did on the bottom face instead of the top face. And then I did my solution. And now we can take a look at the actual results. So if you right-click solution, you can insert deformation, strain, stresses, energy, so on and so forth. And for example, if I right-clicked here and clicked insert deformation total, then I would get this graph, and I could right-click it. And you can see how, as I go through time, for example, let's say right at the beginning, here's what the object is. And if I play this through, the roller goes over it, and you can see the total deformation based off this color bar here. As well as a graph here and a table here. And if you wanted to, you could highlight all of this and export this as a text file or an Excel sheet, and then just do some post-processing on that. Or if you want to take a look at internal stresses, you can also look at that. And if you see here, we have stresses of about 662 megapascals on the surface here. And on the bottom here, we have minimums of about 20. So we do have stress concentrations building up inside our model, which we would have to work with afterwards through cold hardening, or work hardening as it's called. And if you want to look about something else, so let's say you want to know what the strains are. So you can click strain equivalent, right click evaluate all results, and it's evaluating the results. Almost done. And so now you can see what the strains are. And it makes sense that wherever your strains are larger, that's where your stresses are really located. And if you want to save this as a video, you have the option right here, export video file. And you can set the video length, height, current display, adjust things. If you don't want this contouring bands here, you can make this smooth. If you don't want to see the mesh, you can just get rid of the mesh. It's very versatile in how this is done. So let's take a look at what we got as results. So I already showed you the deformations. And you can see that the internal stresses that we got would have to be relieved with work hardening. And what that means is you deal with a slow heat up of your metal to realign the microstructures and get rid of those internal built-in stresses. So that's something you would have to be done. And now to answer the question that I had at the beginning of this little demo was, when cold rolling a piece of metal, how much deformation should you be expected to see in each direction? So one of the things you can do in ANSYS after you've done your simulation is, let's take a look at the take a look at total deformation. We go to the very last time point, retrieve the results. You can actually right click here on this node and you click export. You can export the STL file of the deformed geometry. And if you have that, then you can open it up in SolidWorks, ANSYS SpaceClaim, whatever CAD software you want, and you can actually measure the actual displacements in each direction in millimeters, and then figure out, okay, I know what my starting dimensions were, I know what my ending dimensions are now, and I can see here the beginning dimensions were 1000 by 250 by 100, and my ending size is about 1208, 271, and 70. So my volume was compressed by about 14.5%, and I got elongated in the X, smushed in the Y, and then elongated in the Z as well. So now I can go back and say, okay, now I know how much workable area I have. Is this enough? Should I have moved the roller lower? Should I have raised it instead? Should I add maybe constraints so it can't move too much in the other two directions? And you can answer these things now with simulation rather than actually rolling a piece of metal. So with that, thank you. Do you have any questions or want to see anything else before?
I just feel like I need to practice a lot to actually get the hang of it.
Yeah, this demo is sort of slightly medium, because usually if you look up ANSYS tutorials, you'll see maybe like a simple beam and then you apply a load at one end and you see deformation, which is interesting and all, but it's not like having this, for example, which is more interesting to see and more applicable.
So yeah, one question I actually do have for the sides B and C, it was meant to move in the Z direction, right? Which is normal to the face, but it also moved in the X direction. Was that?
Yeah, let me double check what it was. Yeah. So, which face are you talking about?
B, or in this case,
B.
Yeah.
Yeah. So this is B. So that's displacement 2. So yeah, it's free to move in the Z, which is normal to it.
Mm-hmm.
But it's, no. Oh, I misspoke. It's actually free to move in the X and Y,
Gotcha.
but not in the Z.
Gotcha. That makes sense. Yeah, because it was deforming the other direction.
Yeah, it can deform along this plane of the X and Y, but not in the Z.
Cool. Yeah, it makes sense.
Yeah. It's always hard to think of these three-dimensional coordinates.
Yeah, and that's just Cartesian. Imagine you go cylindrical.
Oh yeah. Oh, you can actually do that. So for example, you click this coordinate system right here. Click insert coordinate.
Wow.
You can switch this to cylindrical. And then if you click this sphere right here, now you have this cylindrical coordinate system. And then you can start doing your boundary conditions based off this instead, if you wanted to. But yeah, any other questions?
Well, if you have no questions, I just want to thank Asad for bringing this part 1, and part 2 will be tomorrow. So if you guys can make it, I think it will be CFD analysis.
Yeah, CFD, which is my bread and butter, and it's going to be based off a arterial aneurysm, I believe. Yeah, so that should be fun.
Sounds good. Well, take care, everyone, and I'll see you tomorrow.